Good evening, everyone. So is my screen visible to all of you?
Yes, sir.
Yeah, and my
Yes, sir.
audio is and my voice is audible, right?
Yeah, yeah.
Okay, so with that, let's start the discussion for today. So, good evening, one and all, to the week one discussion of this course, Computer Vision. And this course was originally taken by Professor Jayanta Mukhopadhyay, Professor Computer Science and Engineering Department, IIT Kharagpur. And myself, Ayan Paul, I am a PMRF Research Scholar from IIT Kharagpur, and I am a TA of this course. By TA, what are my duties? I will solve few questions that are very much similar to your assignment. So, whenever you will be solving the assignment, you will not feel that it's completely new. Okay, so that is only my duty. But before that, what I would like is like half an hour to 1 hour the revision of the week that has been completed, so that will be very much by that it will be very much easier to solve the question. And next thing is at the end, after that we will solve few question, and at the end, if time permits, we will see few of the codes. Okay, so this is how I am planning for all the weeks. Okay, so by this, let's start the session. So fundamental of image processing. So the first question that will arise in your mind is, what is an image? Okay, so what is an image? An image is a structure array of pixels. Okay, so structure array of pixel that you must understood. Okay, pixel values that represent visual information captured from the real world. So we are capturing. Okay, someone is joining. So yeah, people will be joining again and again, so that is why it will get interrupted, so don't mind that. So yeah, so I am, yeah. So what is an image? So in computer vision, an image is a structured array of pixel values that represent visual information captured from the real world. Okay, and what is a pixel? Pixel, the smallest unit of an image representing the color or intensity, is known as pixel. Okay, so that is the two definition you must always keep in mind. One is image, and another one is pixel. So image, again I am repeating, it is a structured array of pixel. Array is a collection of numbers. Okay, so it is a collection of different pixels. Okay, so pixel, smallest unit of an image, is known as pixel, and what it does collect, it collects the intensity. Okay, intensity or the color information of that image. Okay, so each pixel in the image hold the intensity, so this you must always understand. So let's see, this is an image. Okay, this whole thing, this is an image. So if we take a small portion of an image marked by this rectangular portion. Okay, again someone is joining. So marked by this rectangular portion. Okay, so this is the zoomed part of that rectangular portion. Okay, so again, if we are zooming it and we keep on zooming it, this zoomed part is nothing but your 2D array of integers. Okay, so that is why we are calling image, image is represented as matrix or tensor. Okay, so array is collection of numbers, generally known as array. Then there is a something called tensor. Okay, tensor can be of various form. 1D tensor is known as scalar, 2D tensor is known as this matrix, and 3D tensor is commonly called as tensor. Okay, so that is why we called image as a collection of or as an array of integer. And this array we are representing in the form of matrix if we are dealing with only a 2D array. There can be a 3D array also that will discuss. Okay, yeah, yeah. So So yeah, so there are different form of images. Like the image that I have shown here is, this is a grayscale image. What is the idea of a grayscale image? It has only one channel. Okay, one channel. Each pixel, see, or this channel consists of this one channel consists of different, you can say, parameter. One is the width of the image parameter, that is this. Okay, one is the height of the image parameter, height of the image, that is this. These are the two. And next is number of channel. Whenever we are talking about grayscale image, there is only one channel. One channel means it is only a 2D array, that is, it is only a matrix. But when we are shifting from this grayscale image to an RGB image, in RGB image we have this three channel. You can see this is a RGB image, this is a red, green, blue image, the image that you normally seen everywhere. This is a RGB image. Okay, so RGB image has this three channel, red, green as well as blue. Okay, so that is why it is known as RGB. Okay, someone is joining. Okay, so yeah, that is why it is known as RGB image. Okay, so RGB image, earlier we have only one channel for this grayscale image, but RGB image we have three channel, red, green as well as blue. When we combine this three channel together, we get this RGB image. So that is the only difference between a grayscale image and RGB image. There is another type of image known as binary image. So binary image is a special case of the grayscale image. So I have told you grayscale image has this number of pixel forming the row. For example, it is a, let's say it is a 32 cross 32 pixel image. That means 32 in the row and 32 pixel in the column. Okay, so let's say this. So in 32 cross 32, each one cell will consist of a value from 0 to 255, because popularly we are dealing with a 1 byte image. So 1 byte means 8 bits, so 2 to the power 8, that means 256. So in computer vision or simple computer, we always represent this intensity from 0 to 255, not 1 to 256 but 0 to 255. So that is how a grayscale image. So each cell can consist of a number between 0 to 255 in a grayscale image. Now how binary image is a special case of this grayscale image. Binary image is a special case of grayscale image because each cell will have value either 0 or 255. Okay, 0 or 255, that is, okay, not 0 or 1 but 0 or 255, that is either black or white. Okay, 0 means black, 255 means white. Okay, so this binary image is a special case of your grayscale image. Then we have seen this RGB image. There are also different kind of multispectral or hyperspectral image. So RGB image has three channel, but if an image has more than three channel, it is known as multispectral or hyperspectral images. Okay, so that is regarding the images. Okay, so any doubt in this slide, guys? Yeah, any doubt in this slide? What is an image? What are the different type of image? How an image is represented in the form of pixel? What is the difference between a grayscale and this RGB image? And then what is this binary image and this hyperspectral image? So no doubt, right, in this slide? So
Hello.
yeah, please.
Sir, if you don't mind, can you
Yeah.
please record this session and
Yeah, yeah,
after
yeah.
end?
Yeah, yeah, it will be recorded. It will be recorded and posted in a YouTube channel. The link I will give you. Okay?
Okay, sir.
Okay.
Sir,
Yeah, please.
in binary image, pixel is 0 or 1
0
or
or
1.
255. 0 or 255. It is just a mistake there. 0 or
Okay.
255. 0 means pixel value 0 means it is black. 255 means pixel value 255 means it is white. So that is why
But
black or white.
why 256 not? Because 0 से हम consider इसलिए.
Yeah, we have to do from 0 to 255, not 1 to 256. Actually, a pixel is generally represented by 1 byte. Okay, 1 byte means in computer 1 byte means 8 bits. So 2 to the power 8, that is 256. So that is why 0 to 255, not 1 to 256, because in computer the digits start from 0. So that is why 0 to 255. Okay.
Yes.
Sir, Sir, 3 channel image, what is the pixel range, sir?
Can you please repeat?
The 3 channel image, RGB.
RGB, yeah, RGB, same. Pixel value from 0 to 255. Each R red, green, or blue. The pixel value is from 0 to 255 only. Okay,
Okay, sir.
red
Okay.
means, yeah, that will be a different reason. Green means that will be from 0 to 255. It will be a different reason. Blue means different reason. Okay, within
Okay,
0
clear.
to 255 only. So you got it right. What is an image and what are the type of image? It is very important because it is the basic of your computer vision. Okay, so let me assume you got it. Now let's move on to the next things. Okay. Yeah, so now image file. Now we have talked about, we have discussed about image. Now, how an image is stored in a computer. So image file is a digital representation of the visual scene stored in the computer. So image, we cannot have image here and there. We have to store it in a place. Okay, so how we store in a computer? We store in a computer in the form of an image file. So this is a typical representation of image file. So here we have three section: header, then there will be a stream of pixel, and then EOF. So these are the three major section of this image file. Now header, the header contains metadata about the image. Okay, so metadata, what type of metadata? The width of the image, that is number of pixels along the x-axis. Okay, width means x-axis. Height, the number of pixel along the y-axis. Components, that is number of components, or you can say number of channels. So RGB means 3 channels, grayscale means 1 channel, and there can be more than 3 channel also. Then bytes per pixel, that is important. So number of bytes that is used per pixel. So usually we use 1 byte per pixel, so that is why 2 raised to the power 8, that is 256. That is why we represent each pixel from 0 to 255. And then there are other type of thing like compression type, color speeds, etc. Okay, someone is joining. Yeah, so this is the thing about header. Then the middle part, that is stream of pixels. So stream of a pixel, we from the header part we get the metadata like height and width, etc. And now in the stream of pixel we are storing the pixel values. Okay, so after the header, the actual image data pixel is stored. This is a type of long stream of bytes or values that represent pixel colors in a specific order. Okay, so nothing but here we are generally knowing the metadata like width of the image, height of the image, number of this channels, etc. Now all the values are placed in this stream of pixel part, and at the end we have this EOF, or the end of file. So this marks the end of the image data. It tells the system or program that no more pixel data follows. That means end of the file, that is EOF. So again I am repeating, image, you are taking image but you have to store it somewhere. So we store in the computer in the form of image file. Image file has three section: header, stream of pixel, and end of file. Header is the first part. The header, it contains the metadata of the image like width of the image, height of the image, number of channels, etc. Then we have this middle part or the body, that is stream of pixel, that collects the after the header, it collects the actual image data or pixel that is stored. That means the values. Okay, the values, the pixel values, that is important for building the image. So that is collected in the stream of pixel, and at last we have this end of file. This marks the end of the image data. So we have this three section to cover the image file. Okay, so I hope this is clear to you all. This is a simple thing. Only you have to remember three section: header, stream of pixel, and the end of file. Okay, so this is about the image file. Now let's move on to the standard image file format. So this table I have given for all of your convenience. Okay, so you all have heard about different format like JPEG is very common, so it is used for photography, but you have to understand that it is a compression quality image. Okay, so JPEG is there. Then PNG, it is very much famous, that we do for any logo or etc. You are making. So what you want the background to be transparent. So for that we generally use this PNG type of image. Okay, This is the spatial thing. Then WebP, also you must have heard that web picture format. Any image that you are randomly downloading from Google, etc. Most of these images are web picture format. So the important thing about this, that the memory of this WebP is lesser than your PNG or JPEG. Okay, so this is WebP. There is also a format called TIFF that is very much used for making graphs, etc. So it is it is also a it is also flexible, and the dot per inch, that means DPI of the image is very much DPI value is very much greater in TIFF image. So any good quality image that you are using in research or anywhere, you use this TIFF format. So there are different format, you can probably read it after the class. So this thing will be given to you. So these are the standard image file formats. Okay, now let's move on to the geometric definition of an image. So image is an impression of the physical world, a spatial distribution of the measurable quantity encoding the geometry and material property of the object. Okay, so this you can see this is the image formation in the optical camera. Okay, so this is a tree, and if we are forming that image, if we are focusing on this point, so the light will be reflected from this point, it will be focused it will be passing through a lens, and it will be the image will be formed on the image plane. Okay, so this is the object plane and this is the image plane. In between there will be lens will be there. So that is how the image will be formed. Now there are different rules of projection, like perspective projection, parallel projection, and other imaging principle. So perspective projection is the most common type of projection that you can see in all the cameras, etc. So image point formed from the intersection of ray from a point P passing through the center of projection O from the image plane. These things we will learn in detail also in the coming classes, but just you can say this is the perspective projection. So what happens in the perspective projection is the image formed in the image plane in an inverted manner. Okay, so this is the characteristics of this perspective projection. There is another type of projection known as parallel projection. So parallel projection means image points formed by intersection of parallel rays within the image plane. So that is parallel projection. So whenever you are taking this X-ray, etc., there you cannot you do not want this inverted image. Okay, so that is why there we are using this parallel projection. There are other imaging principle also used in this scan radially, etc. So like LiDAR, light detection and ranging. So what we are using is we are using a transmitter, we are using a receiver. TX means transmitter, RX means receiver. So by that we can find out the distance between distance of the point. How? Because we know the speed of the light, and speed equals to distance by time. Speed we know, distance we have to measure, and time also we get to know, because the moment it is the moment you are transmitting the signal and the moment you are receiving it, the time duration you know. So speed you know, time you know, you can get the distance. So this is the three different imaging principle, or you can say rules of projection. Okay, all these things we will study in detail in the coming classes, but this is the basics overview of it. Okay, so up to this the image portion is over. So is it clear?
Can you please explain, repeat the other imaging principle?
Yeah, other imaging principle like LiDAR is there. You must have heard about LiDAR, light detection and ranging. LiDAR, okay? LiDAR. So what we do in LiDAR is we have a transmitter, we have a receiver. So you can see this, there is a transmitter and there is a receiver, okay, RX. Okay, so transmitter, we are emitting a signal in the form of light. LiDAR means we are using the light detection and ranging. So we are using a light signal. So transmitter, we are transmitting this light. Okay, the light will fall on a surface and it will get reflected and it will be cached by a receiver. Okay, so this is the principle. Now you know speed equals to distance by time. Okay, speed equals to distance by time, d by t. That is speed equals to distance by time. So LiDAR, etc., what we are interested in finding the distance. Okay, speed we know because the light which is traveling, so speed we know. time we get to know because the moment at let's say the moment we are transmitting the signal, it is t1. Okay, the moment we are receiving it, it is t2. So t2 minus t2 minus t1, we are getting the time. Okay, so time we know, speed we know, so we can get the distance. Okay, so that is the principle of lidar. So that type of thing we can use, like to understand the distance between the point of the transmitting or receiving signal to the surface. Okay, so that is the principle of lidar. So these are some other imaging principle. Okay, so this is the thing. So is it clear to all of you?
Hello, sir.
Yeah, please.
Sir, in other imaging principle, there is one example, echocardiogram. Can you please explain that?
Yeah, ECG means same thing. That is how the moment you are transmitting the light. So actually ECG, what you have the movement of some thing. Okay, like movement of not ECG, it is I think ultrasonograph. So ultrasonograph means you are detecting if something is there and it is moving or not. Okay, so that is the concept of this ultrasonograph. So there also we use this principle, like we are transmitting a ray of light and we are receiving it, and we are seeing that it is moving or not, it is stable or not. So by that we can do the analysis. Okay, so that is how we are doing it. The type of light is different, like we ultrasound means we are using a ultrasonic ray, so that is why we can also get the image that is inside the structure or anything inside our body. Okay, so that is the principle of this ultrasonograph. Okay.
Okay.
So let's move on to the next part. Okay. So the few concept and operation regarding to image. So first thing is image histogram. Okay, so this is the image, and okay, let me move this. This is an image. Okay, and this is the image histogram. So what is an image histogram? It is a graphical representation of the distribution of pixel intensity. So I have told you the image is a 2D if it is a grayscale, then 2D array of integers. Okay, so this 2D array of integers we have different pixel occurring different times, like there in this d into d cross d, like let's say this is the okay, so d cross d image, so we have d number of pixel in the row and d number of pixel in the column. Now each pixel, like 0 is occurring how many times, so that is the frequency of this 0 pixel. Then 1 is occurring how many times, that is frequency of 1. Like 200 is occurring how many times, that is frequency of 200 pixel. Okay, so that is how that is the image histogram. So image histogram, how we are plotting it, in the x-axis we are keeping the pixel values like 0, 1, 2, 3, 4 to 255. Okay, and for frequency, how many times the 0 is occurring. Okay, so that then how many times with this 1 is occurring, how many times 2 is occurring, like that. So by that we can plot this graph, and this graph is known as image histogram. So again I am repeating, image histogram is a graphical representation of the distribution of pixel intensity, brightness of color values in an image. It shows how many pixels in an image have a certain intensity value. Okay, someone is joining. Yeah. So yeah. Yeah, so this is the thing, like how many each pixel is occurring how many number of time. So that is this image histogram. Okay, again someone is joining. Yeah, so this is the image histogram. Now there is a concept known as binarization. So binary image, I have already told you what is a binary image. Pixel is either 0 or 255. So that is binary image. Now if we convert any image to a binary image, So that is known as binarization. Okay. In case someone is unmuting his volume. Okay, so guys, it is better to mute unless you are asking a question. It is better to mute. Okay, so it will be easier for other audience. Okay. Okay. So yeah, binary image. Yeah. So I have already told you what is a binary image. In a binary image, the pixel value is either 0 or 255. Okay, 0 means black, 255 means white. So in this picture, you can clearly see there are either this black color values that may not be 255, that may be 200, etc. 200, 201, etc. like this. Okay, and there is a background. Like, background values are very much close. It is a background is white. So that means background values are very much closer to this 255. Okay. Okay, so okay, let me again clear it. So yeah, you can see this. So there are two parts. Okay, background and foreground. Foreground, something written on it, that is foreground, and there is a background. Okay, the white page is the background. So foreground and foreground, we have this dark pixel. Dark pixel means values are very much closer to 0. Then we have this background. Background means white. White means the values are very much closer to 255. So that is what. So foreground, the part we care about is known as foreground. In our case, the part we are caring about, that is the text we are caring about. So that is represented by dark pixel, very much closer to 0. Then we have this background. Background, the surrounding or area we want to ignore. Okay, in our case, the background, it is formed by bright pixel, that are values very much closer to 255. Now how we binarize it? It is very much easy how to binarize it. The dark pixel or the foreground, we are making it exactly 0. The light pixel or the bright pixel, we are making it exactly 255. So that is how we convert a grayscale image, or we convert a we convert a grayscale image to a binary image. This process is known as binarization. Now the spatial the binarization with some threshold. Okay, now your question is what is the threshold at which we will like, there is a pixel value 200. Okay, so this 200 how we know that 200 will be closer to 0 or 200 will be closer to 255? Okay, how we will decide it? So for that we use a term called as threshold value. Okay, so what we do is, if the pixel value is lesser than threshold, then we consider it as a foreground. Okay, and we will convert it to 0 or black pixel. If the pixel value is greater than or equal to this threshold, so we will term it as white or the background pixel. So two threshold here is used in this image. One is 156 and one is 192. So in 156, what is happening is, if the pixel value is less than 156, those pixel value we will change it to 0. That is, we will darken it. The pixel value which is greater than equal to 156, those pixel value we will convert it to 255, that is white. Okay, so that is how we are doing this thresholding process. Now this is a thresholding to 192. Now in 192, you can see the values are the foreground is more dark, but what happens is the noise is also coming. Okay, so this is the trade-off. Okay, if we increase our threshold, what will happen is our foreground will be more dark, but what will happen is because of that we will get more noises. Okay, and if we lessen the threshold, what will happen is the pixel value will be the foreground will be less dark, but there will be less noise. So this is the trade-off. So this is the concept of binarization and thresholding. Okay, so is it clear to all of you? Image histogram, binarization and threshold. This is a basic concept and it should be clear to you. Yeah, please.
Sir, threshold value 156 and 192. Can you please explain that?
Yeah, that is up to you. Okay, threshold value, one threshold value, you just keep one threshold value. Okay, it is not an automatic thresholding, but it is a customized thresholding. Okay, so let's say you are keeping the threshold value 156. Okay, let's say. So what will happen is the pixel value that will be lesser than 156. We will keep it. We will round it off to 0. That means we will blacken it. Okay, pixel value less than 156. We will round it off to 0, and we will blacken it. The pixel value which will be greater than or equal to 156, we will brighten it, or we will be rounding it off to 255 or white. So that is background. Okay, so that is the thing. Similarly, you can choose another random value like 192. Pixel value lesser than 192, you will round it off to 0. Pixel value greater than 192, you will round it off to greater than equal to 192, you will round it off to 255. Okay, so this is the thing. So this is random value you are choosing. Okay, now if you will lessen the threshold, or if you will decrease the threshold, what will happen is your foreground, or the things that you are interested in, okay, the foreground, because text we are interested in, that will be less bright. But what will happen is, as your text is less bright, you will have less noises. And if we increase the threshold, what will happen is the text value here is more dark. But what will happen with that is you will also induce noises. Okay, you can see the noises coming over here. This picture is more clear. This texts are dark, but noises are also coming. So that is thresholding. So is it clear to all of you? It is a very basic principle, so please ask me
Yes,
if
sir.
it is not clear. Is it clear? Anyone with any doubt how image histogram is formed? So is it clear how image histogram is formed? Clear, right? Please ask if any doubt is there, because it is one of the basic thing of image. You should know it, image histogram. Clear, right? What is binarization? Just converting a grayscale image to a binary image is known as binarization. Binary image means either the pixel value is 0 or 255. So that is binarization. Now what is this thresholding process? We choose a random threshold value. The pixel value which are less than threshold, we rounded it off to 0. The pixel value which is greater than equal to threshold, we round it off to 255. So that is thresholding. Okay. Okay, so I hope it is clear to you all. Okay, so let's move on to the next thing. So let's move on to the next thing. So in the previous slide, what we have discussed is random thresholding, but now we will be focusing on this automating thresholding. Means the threshold, if we can get this threshold value automatically, okay, so that will ease our process. So for that there are two algorithms. One is this Bayesian classification, and second is this Orsu thresholding. So what is this Bayesian classification? Now in the previous slide I have told you about image histogram, that is brightness value or intensity value in the x-axis and frequency in the y-axis. Now if this frequency is divided by your cumulative frequency, then you will get probability. Okay, if frequency will be divided by this cumulative frequency, then you will get this probability. Okay, so this is the probability. So it can be easily computed. So if you have x and if you have frequency, so frequency divided by cumulative frequency, you will get the probability. Okay, so this is a advanced form of your image histogram. Okay, now what we do is, again, thresholding means what we are doing, we are separating the image into two classes, foreground and background. Okay, so let's say W1 is your foreground. Okay, foreground means the thing that we are interested in, like text. Okay, background means that the things we are not interested in, like the background behind the text. Okay, so that is W2. Now here what we will do, we will be computing a threshold with the help of something known as Bayesian classification. Okay, so how we move? First we will again choose a random threshold, like let's say this is our threshold for now. The area before this threshold, we are considering it as W1 class. The area after the threshold, we are considering it as W2 class. Okay, now Bayes theorem, you all know, that is P class given by the pixel equal to probability of the class into probability of pixel given the class divided by the probability of the pixel. This is the Bayesian classification. Why we do Bayesian classification? Because PW we get to know, Px by W we also get to know, Px we get to know, but PW by X is difficult to find. That is why we use this Bayesian classification. Okay. Now how Bayesian classification? We have to assign this pixel to W1 if PW1 by X will be greater than PW2 given X. Okay, else to W2. If this condition is satisfied, we will be assigning it to W1 class, otherwise W2 class. That means wherever this PW1 by X is greater, we will assign to this class, otherwise we will assign to this class. Okay. Now for this, if we compare this PW1 by X or PW2 by X, Px is common in both the side. So just by calculating this part, we can get the answer. Okay. So how this how this can be solved? See, PW and Px by W we still don't know. So for that we use an algorithm known as expectation maximization or EM algorithm. Okay. How the EM algorithm work? EM algorithm basically it find out your Px by W. Okay. So this can be found out by this formula. Okay. So this can be easily find out by this formula. And once you know that, if you will if you okay, someone is joining. Yeah. So once you know this thing, once you know this thing, Px by W, Px by W, once you know, you can find out this PW1. How? Because this if you this X will be from 0 to your threshold. So 0 to threshold, threshold, if you will integrate it, this probability values, you will get the PW1. Similarly, 1 minus PW1 will be PW2. Now now this there's a formula for mu1 sigma 1 square, mu2 and sigma 2 square. So by that you can find the this Px by W. Okay, so this is nothing but this is the formula of Px by W. Okay, this thing. Okay, Px by W. So by that you can find the Px by W. So now how you can compute the new threshold value? For X lesser than threshold value, if your this condition if this condition PW1 greater than PW2X, then this condition satisfied, otherwise you have to change the threshold. Okay, and you have to keep on iterating. So this is the you can say this is the algorithm expectation maximization. So by this you can automate the threshold. There is another automating threshold process known as Orsu thresholding. So Orsu thresholding, again, how it choose the threshold? It choose the threshold value which maximize the in class variance between sigma b square. So there's a class variance called sigma b square, and it calculates this. This is the formula of sigma b square, pw1 into pw2, u2 minus u1. What is u2 and u1? Yeah, so expectation maximization, it assumes that the curve that is forming, it is nothing but a Gaussian distribution or normal distribution. Okay, this is the formula of Gaussian or normal distribution. So u2 and u1 can be calculated by this thing only. Okay, u2 and u1 can be calculated, and wherever sigma b square is maximizing, we will have to choose that threshold. So these are the two process of automating the threshold. Okay, so just remember this. Don't no need to go into formulas and all. Just remember this. Thresholding we know. Now we have to automate threshold. Now for automating threshold, we are using this two principle. One is this Bayesian classification, and second is Orsu thresholding. So by this we can get our automatic threshold. We do not need to feed the threshold, but we can get the threshold by its own. So this are the two method of automating threshold. Okay, so this is the thing. Okay, formula and all, no need to go into formula and all. Just now we can understand the concept as of now. Okay, so this is the thing. So is it clear to all of you? Okay. Okay. Okay, so let's move on to the next thing. Okay, so yeah, there's a contrast. Yeah, so before that, histogram equalization is important. So histogram, you all know histogram, but what happens is, let's see this image. Whenever we are plotting the histogram, so histogram, what is in x-axis? X-axis is pixel value 0, 1, 2 to 255, right? And what is this y-axis? Y-axis is the frequency. So you can see this image very well. So what is happening is, this image is very dark because you can see the frequency, the pixel values which has greater frequency, that is only in this much range. Okay, like let's say this is like 25 to like say 100. Yeah, 25 to 100. So all the pixel are in 25 to 100 range. Okay, other places it is empty. That means other places we do not have pixel values. Okay, so if we can just widen this, or if we can stretch this curve. Okay, stretch this curve, what will happen is, our there will be a contrast enhancement technique. Okay, so that is the main purpose of this histogram equalization. So if we can equalize the image so that every pixel gets some of the pixel values, unlike here what is happening is, from 25 to 100 we are getting more frequency. Elsewhere the frequency is 0, but here you can see for it is stretching. Okay, so up to 200 or to 25 we are getting some amount of frequency for each pixel. So this technique is known as the contrast enhancement, and the process what we are doing it, that is known as histogram equalization. Okay, so histogram equalization is a contrast enhancement technique in an image that redistribute the intensity values of pixels so that they spread more uniformly across the available range. Okay, so they spread more uniformly. Earlier the pixel values were only from 25 to 100, let's say, but here you can see the pixel value is starting from, let's say, 5 to 200, 220, something like that. So by this what will happen is, earlier this was our image, now our image is this. So we are doing the contrast enhancements. Okay, so that is contrast enhancement. Okay, so contrast enhancement of pixel mapping means converting each original pixel intensity to a new intensity to improve the contrast, done through mapping function that is derived from the image histogram. So we will also solve a question related to this, so thing will be more clear. Okay, but I hope this is clear. Histogram equalization. Okay, the concept is clear. Earlier what is happening is, our intensity is distributed in a very short range, but now our intensity is distributed in a wide range. Okay, so by that what we are doing, our image gets this contrast enhancement. Okay, so this is the thing about histogram equalization. So is it clear to all of you? Clear, right? Okay. Okay. Now, yeah, segmentation. So binarization we have done. Now the special case of binarization, or you can say the elder brother of binarization, is the segmentation. Okay, so what is this segmentation? Segmentation is the process of partitioning an image into non-overlapping meaningful set of pixels that corresponds to distinct structure or reason. So earlier what we are doing, we are choosing one, like this is your graph, like this is your graph. Okay, earlier what we are doing, we are choosing only one threshold. The threshold before that we are assigning it to 0, threshold after that we are assigning it to 255. Now what in segmentation we can do is, we can choose a different type of threshold, like you can choose two or three, you can choose more than two threshold. Okay, so that is known as segmentation. Now each threshold we are choosing, what we can do is, we can give a different color to this threshold. So by that our image, okay, someone is joining. By that what we can do, we can extract this meaningful set of pixels. Okay, so that thing is known as multi-level thresholding. Okay, segmentation is also known as, again someone is joining. Yeah, segmentation is also known as this multi-level thresholding. Okay, this multi-level thresholding. Like example, it will be much clear. So this was our original image. Okay, this was our original image. Now we are doing the segmentation. So we have segmented into three parts. So two threshold we are using, that means we are getting three parts. This is first threshold, this is second threshold. So for this part we are giving a let's say we are giving blue color. For this part from pixel value 61 to 119 we are giving a green color to it. From 120 to 255 we are giving a yellow color to it. So by this our image will be changed from this to this. So by this we are what we are doing, we are getting meaningful set of pixel. That means the dark portion that we are getting, that is one like okay. So so dark color we are getting, that is 0 to 60. Okay, so 0 to 60 that we are giving it by a blue color. So this is actually a map. So blue color means it is water. Then 61 to 119 we are giving it a green color. So that is some kind of, let's say, some kind of vegetation, etc. 120 to 255, that is bright color. So that is, we can assume it's some kind of land, etc. So that is multi-level thresholding, that is known as segmentation. And binarization is nothing but it is a simplest form of segmentation. Binarization means we are only choosing only one threshold, but more than one threshold if we are choosing, that is known as multi-level thresholding or known as segmentation. Okay, segmentation means same multi-level thresholding, but we are also giving colors to each threshold to derive a meaningful set of pixel. Okay, so that is multi-level thresholding and segmentation. Okay, so is it clear to all of you? I think it is clear to all of you. It is an easy concept. Okay, nice. Yeah, so let's move on to the next thing, that is component leveling. So component leveling, how we are doing a segmentation. So segmentation, previously what we are doing, we are choosing some kind of threshold, like two threshold we are choosing. Two threshold means three part. Okay, again someone is joining. Yeah. So thresholding, by this multi-level thresholding, what we are doing, we are choosing different threshold. We are parting the image into this like two threshold means three part, and we are giving color to it. But we can also do this technique called component leveling. What does component leveling do? Component leveling is a process of identifying connecting regions component in an image when neighborhood pixels share the same level intensity. Now, if the image is sharing the same level or intensity, those pixel only we are connecting it, and we are calling it as component leveling. So earlier what we are doing it like 0 to 50 we are giving 0 to 50 we are giving like this blue color. But now what we are doing, the pixel value which are same, like 20 20 20 20, these are same. So for this we are giving one color, like 50 50 50 50 50. For this pixel we are giving this green color. 100 100 means same level, the 100 and 100 or same intensity, we are giving this purple color for purple color. And this 2020 we are giving this pink color. Okay, so this is component leveling. So in component leveling, one important concept is neighborhood. Okay, so if we choose a pixel, okay, so the pixel has neighbors. Okay, because this pixel is surrounded by other pixels. Okay, so that are known as neighbor of the pixel. So there are two neighborhood rules. One is known as 4 neighbor, one is known as 8 neighbor. Whenever we are talking about the 4 neighbor, so what we are interested in, if this is our target pixel, so what we are interested in, the pixel above that, the pixel below that, the pixel left of this, and the pixel right of this. But whenever we are choosing the 8 neighbor, so apart from this 4 neighbor, we are also choosing the diagonal pixel. So that is 8 neighbor. So that is how we are doing the component leveling. So how component leveling is done? Treat the image like a graph. So yeah, your image is a this array. Okay, array of values. Okay, someone is joining. Yeah. So your pixel is a array of 2D array of different values. So each pixel is a node. So we consider each pixel as a node, and edges are found between the neighboring pixel that have same intensity. So we will form the edges, the pixel having the same intensity but neighborhood. Okay, now this is also 100, this is also 100, this is also 100, this is also 100, but somehow we cannot join it because these are not neighbors. In between there are other pixel. Okay, so that is why in between we cannot join it. So this is known as component labeling. So component labeling, this neighborhood concept is also very important, because in between if other pixel is coming, we cannot join this pixel. So that is known as component labeling. So that is how we can also do the segmentation. Okay, so this is our technique of segmentation only. So these are different component leveling technique. Okay, these are different component leveling technique here shown. Okay, so this is our original image, this is our this segmented image, and these are different different component leveling technique. The this picture, let's say the intensity values that is shown in white, let's say it is 200. So 200 values all are shown in white. Here here you can say that 110 values are shown in white. Here like 100 value are shown in white, like that. So this is known as component leveling. Okay, so is it clear to all of you? Okay, so now we will be moving to
Excuse me, sir.
yeah, please.
Sir, sir, why we need the component labeling and what the real life use case of component labeling?
Component leveling, if we need to know the same intensity pixels. Segmentation, what we are doing, we are similar intensity pixel, we are grouping it, but same intensity pixel if we need to group it, we use the component leveling. For example, you are taking a satellite image, and if you are focusing a certain kind of, let's say certain kind of vegetation that have this pixel value at 200 only. Okay, so for that purpose you can use component leveling. Segmentation can be done for 0 to like 190 to 210, there you can do the segmentation. But 200 pixel if you want to 200 pixel if you want to like mark, for that you can use the component leveling. Okay, also component leveling use this neighborhood technique. So the plant species with 200 label that are very close to each other, that only it will segment, other it will not segment. For example, a tree value having a plant species value having 200 intensity, that is far away, so that it will not segment, because it will only segment the neighborhood values only. So that is the use case of component leveling. It is a specialized case of segmentation only. Okay, is it clear? Okay.
Yes, sir. Yes, sir.
Okay, so let's move on to the next thing, that is gradient operation. So in an image processing, gradient represent change in intensity, essentially edges. So how an edge of a picture, like you are given a like a image of a monument. Okay, so you want to know the edges. So how the edges can be find out in this image processing is, there is a sudden change of pixel value. For example, the pixel value as at x minus 1 comma y is like 200, and pixel value at x comma y position will be like 80. So there is a huge change in the intensity. So for that the gradient operation is very important. Okay, so it essentially find the edges. So to find the edges, we use this derivative marks filters to compute the rate of change in pixel intensity. Now if you are given a normal image, the intensity, the change in intensity cannot be shown very abruptly. Okay, because normally the change in intensity does not seen without the use of mask. What is the use of mask means? Use of mask means like you have a 32 cross 32 image, but now you are using a mask 3 cross 3. Now by using this mask 3 cross 3, you are changing the intensity very much. Okay, so by that what will happen is, using that mask, now there is a sudden or abrupt change in the intensity. So by that you can find out the edges. So this is the purpose of this gradient operation. Okay, so this is the formula of gradient. You all know this is the formula of gradient, that is del f by del x for this I cap, that means x direction, del f by del x, and del f by del y j cap. Okay, del f by del x means you are doing the partial differentiation, not the complete differentiation. So this is just a formula. So these two operators are very much common in the edge detection, that is Pritchett operator, and another one is Sobel operator. So I have told you, normally we cannot find the change in intensity without having the mass. So what this Pritchett operator, or what this Sobel operator do is, it gives us this mass values. Okay, so these are the mass value for this Pritchett operator, and these are the mass value for this Sobel operator. Okay, so this mass value you have to keep in mind, because question generally comes from this. So this is the horizontal operator for this horizontal mass for this Pritchett operator, and this is the vertical mass for this vertical mass for this Pritchett operator. Similarly, this is the horizontal mass for this Sobel operator, and this is the vertical mass for this Sobel operator. So what is the difference between the Pritchett and Sobel operator is the value of mass. Okay, so in this both this case, what you can see is, here you can see for this horizontal operator, the middle all this is 0. Okay, and vertical operator, the middle column is 0 for this horizontal operator, the middle row is 0 in case of this Pritchett vertical operator. But when you are talking about this Sobel operator, again middle is 0 for both this, but here you can see the change in weight. Here all this have equal weight, that is 1 1 1. But here you can see the difference in weight. This row has 1 weight, this row has 2 weight, and this row again has this row again has 1 weight. Similarly, this column has 1 weight, this column has 2 weight, and this column has 1 weight. So if we are talking about this Pritchett operator, all rows, columns in each direction have equal weight. Okay, so all have equal weight, 1 1 and 1. But here you can see the middle row has 2x weight. Okay, so Sobel operator most robust to noise, because it has more important to the central pixel. The central pixel we are giving more weight, like this is the central pixel, so we are giving more weight in case of Sobel operator. Pritchett operator, we are giving equal weight to all the columns as well as rows. So that is the difference between the Sobel operator and Pritchett operator. Also, the total maximum gradient here is 6. That is, if you will do the absolute sum of all the values, that is mod of -1, mod of -1, mod of -1 plus 1 plus 1 plus 1, that is 6. Similarly, you will do the 1 plus 1 plus 1 plus mod of -1, mod of -1, mod of -1, again that was 6. Okay, so the absolute sum for this mask is 6, but here the absolute sum will be 8. So that is why this Sobel operator has Sobel operator is 8 times that of gradient. Here the Sobel operator is 6 times that of gradient. So that is the thing. So again I am okay, someone is joining. Yeah, so again I am simplifying it. So in this slide, what we are discussing the gradient operation. Where we use this gradient operation, we use this gradient operation to find the edges. Okay, so what happens is, how the edge can be found in an image if there is a sudden or abrupt change in the intensity of the image. By that we can know that there is an edge present. Okay, so for that simple image we cannot do it. We have to first use a mask on an image, and after using a mask on an image we can do this do this operation of gradient, so that becomes more you can say more visible, otherwise it won't be visible. In normal image if we do the gradient operation, it will not be visible. So for that, for having the mask, we have this two things: one is pre-width operator and second is Sobel operator. So these are the horizontal mask for this pre-width operator, and this is the vertical mask of this pre-width operator. This is the horizontal mask for this Sobel operator, this is the vertical mask for this Sobel operator. Okay, the difference between this is in pre-weight operator we are giving equal weight to all the rows as well as column, but here in the central row or column we are giving 2x weight than the first or last row or column. Okay, and here if we do this absolute sum, it will come 6. Here if we do the absolute sum for this, it will come 8. So this is an example. By this we will get the vertical gradient, by this filter we will get the horizontal gradient, by this filter we will get the vertical gradient, and if we will do the resultant of this, that is root over x value, x square value plus root over y square value, we will get the resultant. So this picture is not clear, but I will show you in the form of code, so that will be more clear to you all. Okay, so this is the concept. So is it clear? Is it clear to all of you?
Sir, can you please explain one more time computation with a mask?
Yeah, computation with a mask. Yeah, mask is nothing. Mask is a convolution filter, means there is a 32 cross 32 image, okay, and there is a 3 cross 3 mask. All this mask you can see in the private operator or the Sobel operator. This is a 3 cross 3 mask. So if you will do the normal gradient operation, so your edges won't be that visible, because the intensity, there is not abrupt change in intensity value, so that is why edges will not be that much visible. So for that what we do is, first step is we do the masking of the image. Okay, so after the masking of the image we will do the gradient operation, so by that our edges will be more clear. Okay, so this is the concept. Okay, so for the masking we have this two type of operator. One is pre-weight operator, one is the Sobel operator. Pre-weight operator, we have this filters, you can see horizontal filter gx and vertical filter gy. The characteristics of this pre-weight operator is all the rows and all the columns have equal weight. Okay, and if you will do the absolute sum, it will be coming 6. Whereas Sobel operator, the characteristics is the middle row or middle column has 2x weight than the okay, someone is joining. Then the middle row or middle column has 2x weight than the first column and the third column, or first row or the third row. Okay, so and again if you will do the absolute sum, it will be coming 8. So that is the difference between pre-weight and Sobel operator. Okay, so is it clear to all of you? Masking means you just do the convolution operation, means some values are already present, you are imposing a mask on it. Okay, so let me show you the next thing, it will be much clear to you all. Okay, so let me show you this. This is a convolution operation. Okay, so masking, what I have, let's say this is the marks as hxy is your mask, and this is your original function fxy, and you are getting the gxy function. So how gxy function can be formed? This fxy function you already have. This is your fxy function, and hxy you will get the weight, like w1 into this pixel, w2 into this pixel plus w3 into that pixel. Like that you can do the masking operation. So this is also known as masking operation or convolution operation. This is also used in a technique known as noise filtering. So image, there will have different type of noise. So to deal with this noise, we have this masking. If we just impose a mask to the image, our noise will be reduced. So generally there are three types of filtering that is used. One is custom weighted average filtering, second is this Gaussian smoothing, and third is this median filtering. Okay, so different type of filtering means it uses different type of your convolution function. Okay, custom weighted average means this is how we are choosing a mask in case of custom weighted filter. For this for this Gaussian smoothing, the mass we are choosing, that will be coming from a Gaussian distribution. So that is why Gaussian filtering. Median filtering means your gxy, or the result that will be median value among the neighbors. So we will choose, let's say 3 cross 3. What we will do, we will find out the median value, and we will replace the center pixel by this median value. So that is median filtering. Okay, so that is median filtering. So these are the three type of filtering that is used. So I have also given a summary table you can look at. So these are the three filters, and that is weighted average filter, that is best for this general noise. If we are talking about salt and pepper noise, so you all know salt and pepper. So if we just sprinkle salt and pepper, so your image will be noisy, right? So that is salt and pepper noise. So for that we are using this median filtering. Also we are using Gaussian filtering for random noise. Okay, so these are some of the characteristics for it, so you can see. So these are all the image operations. So what we have learned so far: what is an image, geometric distribution of image some sort, then image, then what is an image file, how to store the image, and then this geometric distribution. Then what we have seen, different type of operation on an image. So up to this is your image processing complete. Now what we will see is image transform. Okay, so image transform, it is a mathematical operation that converts the image from one domain to another domain. So this transform can be used in signal processing or image processing, and image can also be think of as a 2D signal. Okay, so that is why we are doing the transform. So the image that we have originally had, that is a spatial domain. Okay, that is we have a space, and in this space there are different pixels. Okay, that is spatial domain. So what is our target? To change into a frequency domain. So that is known as image transform. So why we are doing it? To simplify the complex operation like filtering, compression, exact this meaningful feature from this image, and make some operation faster. Because convolution, you can see this convolution operation, it is what? It is multiplication as well as adding. But when we will convert into a frequency domain, what will happen is we will only do the multiplication process. So that is image transform. So let's say this is your image. Okay, this is your image. So we have sigma I, that means this is the one dimension, sigma j, this is the another dimension, bij, this is your this lambda ij into bij, this is your whole function. Okay, so this is how a function is written. Okay, so lambda into bij, lambda is some case of scalar, and bij is a direction to it. Okay, so this is how you write a function. Okay, now how you can do the so let's say this is the orthogonal expansion. So what is this orthogonal expansion is? You are if there is a two-dimension image, so what you are doing is you are transforming it into this two-dimension, but it is a sum of orthogonal basis function. Orthogonal function means both this function are independent of each other. Like if we say about sine and cosine, the sine and cosine function are completely independent of each other. Okay, so that is why this type of function are known as orthogonal function. So generally the basis, this is actually a basis, the direction. Okay, the basis that we select in case of 2D image, that is always orthogonal to each other, because if it is orthogonal to each other, our calculation process will be much simpler. So that is the orthogonal expansion. Again, this is complete theory, no need to get into deep, but this this is the definition that you should always focus. The image transform is a mathematical operation that converts image from one dimension to another. What dimension to what? Spatial domain to this frequency domain. So that is image transform. The others are formula, no need to get into deep, but this is what you should understand, what an image transform is. Why we are doing it? We are doing it to simplify the operation, because earlier if we are keeping it in a spatial domain, our operation are little bit more complicated, but whenever we are transforming it to a frequency domain, our calculation are much easier. So that is image transform. Okay. Now Fourier transform, again Fourier transform is a type of this transform only. It converts the signal image from the spatial domain to this frequency domain, expressing it as a sum of sine and cosine wave. This is important. Now the basis here we are selecting is sine as well as cosine. What we are selecting it because previously, okay, someone is joining. Okay, so yeah, so this is the Fourier transform that I was showing. Yeah, Fourier transform. What is the characteristics of Fourier transform? It is the basis that we are selecting is that is the sum of sine and cosine. Why it is a sum of sine and cosine? Because if it is a sine of as it is as we are expressing it as a sum of sine and cosine. So what will happen is the calculation part is much easy because sine and cosine are orthogonal vectors. Okay, so they are independent vectors. So that is why the calculation part is much easier. So how to now the question is how to do the image transform. Okay. So how to do the Fourier transform? So let fx will be your function. Let this is your function. Now to do the Fourier transform, what you have to do? You have to multiply it with by basis. So actually this is the basis. E to the power j omega x is our basis. Okay. So if a function into e to the power minus z of omega x. So if you just multiply it with the basis into dx and from minus infinity to plus infinity, you will get the Fourier transform. If you are given the Fourier transform, you can convert it into a function. How you can convert it? By your inverse transform. So that is 1 by 2 pi minus infinity to plus infinity fx e to the power j omega x dx. So these two formula you should keep in mind. Okay, so what will come in the question is you will be given a function, you have to convert it to a frequency domain. How you will be converting into a frequency domain? By Fourier transform. So just keep this formula in mind and you will do the calculation. Okay, so what is the purpose of it is to analyze which frequencies are present in a signal image and how strong they are. So we are converting from this spatial domain to this frequency domain. And why we are converting this? Because we want to analyze which frequency are present in the signal image and how strong they are. Now there is a this concept of even odd function and how they relate to this Fourier transform. This is known as Euler's formula. Okay, this is nothing but Euler's formula. Now there are two type of function. One is an even function, one is an odd function. What is an even function? Even function of f minus x. If f minus of x will be equal to fx, then that function is known as even function. If f minus of x is equal to minus of fx, then this is known as odd function. Okay, so this is even function and odd function. Now why we are introducing this this even function and odd function is because you can see this is the Fourier transform. Okay, this is the Fourier transform. So Fourier transform has this two part. One is this cos omega x and sin omega x. Okay. Now what will happen is if you multiply the function with sine of omega x, so that is this part fx into sine of omega x for this even function. So if your function is even and if you are multiplying is by sine omega x, so sine omega x is a odd function because sine of minus x is equal to minus sine of x. So fx, so sine omega x or sine x is a odd function. So this is a odd function, and this fx is your even function. So even into odd will always be odd, and we know by this is if we integrate any function from minus infinity to plus infinity, and if the resultant is a odd function, our value will always be 0. Similarly, cos of x is a even function and fx is here is a odd function. So again the multiplication will be odd function, and again if we do the integration of minus infinity to plus infinity for this odd function, it will come as 0. So that is why this is the analogy to this. So this is your formula of this Fourier transform. Now if it is an even function, this real part or fx cos omega x will be 0. If this is an odd function, then this imaginary part will be equal to 0. So this is the correlation from this to this. Okay, again there's more formula, but if you will only remember this much formula, your purpose will be solved. And this concept that Fourier transform, it converts the time domain to frequency, time or spatial domain to frequency domain with the help of and it is written as a summation of sine and cosine wave. If you just remember this and remember these three formulas, your task will be solved. So this is for Fourier transform. Okay. Now this discrete representation. So why we use this discrete representation? Actually, in real world, all the signal etc. are continuous in nature. Okay, so when the signals etc. are continuous in nature, what happens is it is difficult to perform operation on this. So that is why what we are always doing is we are converting this continuous information to a discrete information. Okay, how we are doing this? A discrete representation of a function means we are taking sample of a continuous function at a regular interval. So in the previous slide, what we are writing fx. Okay, we are writing fx. Okay, this we are writing fx. So that is a continuous function. But discrete, how we can write it? A discrete function n into x naught. So what is x naught? X naught is a sampling interval. Okay, so now we are converting continuous function to a discrete function. So we need this sampling interval. So the x naught is the sampling interval and into number of sampling intervals. So by this we can change a continuous interval into a discrete interval. Like you can see your analog watch, right? So analog watch is a continuous watch, and you also seen your digital watch. So digital watch is your discrete signal watch. Okay, so what is the difference? Analog watch means you can if you are focusing on the analog, so it is a continuous. Okay, but discrete is it will be giving you 1 second, 2 second, 3 second, like that. But analog means it is continuous, totally continuous. So it is actually easy to perform our operation for discrete functions. So that is why we are always interested in converting a discrete information into a converting our continuous function to a discrete function. Okay, so this is the concept. And now there are discrete linear transform. The previous transform we have seen the Fourier etc. That is the continuous function. That is for continuous function. Now will be seeing discrete linear transform. So discrete linear transform is any transform that works on discrete data. So earlier we are doing it on a continuous data, but now this is a discrete data, is linear. Okay, linear means that it follows rules like additivity and scaling. Scaling is nothing but n into something, that is scaling. Additivity, a1 plus a2 a3, that is additivity. So these are the two properties of the discrete linear transform. Now it has this two important thing, that is discrete Fourier transform and discrete cosine transform. What is the purpose? To convert discrete signal images into representation that are easy to analyze, compress or filter. Okay, so this is the thing. Now again nothing to do. Now these are the two things, that is discrete Fourier transform and discrete this cosine transform. So again you have this function. Okay, this is the function fn and you have this basis. Okay, this is the basis. So what I have told you is the e to the power minus basis you have to do whenever you are doing this Fourier transform. Okay, so as this is a Fourier transform, again this but earlier you have seen there is a integration sign because that is continuous function. Now there is a summation sign, that is discrete. Okay, so that is discrete Fourier transform. So this is a discrete Fourier transform and this is a discrete cosine transform. Discrete cosine transform means Fourier means you have both sine as well as cosine. Cosine transform means in this basis function you will only have this cosine term. Okay, this is the thing. Purpose and etc. you can see, but this is the common thing. Okay, this is the common thing that you must understand. Okay, so this is the thing. Now let's move on to the next thing. This is a generalized discrete Fourier transform. Again, not that much important, but This is the formula of this generalized Fourier discrete transform. Again, e to the power minus basis, so this is the basis, and e to the power we have to do the minus basis for this Fourier transform. Now this is the generalized discrete Fourier transform. Generalized means we are generalizing it, we are generalizing the parameter, means there are two parameter here, alpha as well as beta. You can see this is alpha, k plus alpha and beta. So alpha it modifies the frequency side, beta it modifies the time side. So we have different values of alpha and beta. If it is 0 0, we call it discrete Fourier transform, DFT, that is common. If it is 0 and half, this is the odd time discrete Fourier transform. If it is half 0, that is odd frequency discrete Fourier transform. Half, this is the odd frequency odd time discrete Fourier transform. Again, not that much important, but this you just remember that there are two parameters in this discrete Fourier transform. One is alpha and another one is beta. Alpha it modifies the frequency side, beta it modifies the time side. So this much you can remember and your purpose will be solved. Okay. Now this is the convolution multiplication property. So I have told you, let's focus on this only, CMP for Fourier transform, that is important. So I have told you convolution previously that we are using, that consists of this multiplication as well as this addition process. Okay, so that is true process. But when we are converting from this time domain or spatial domain to the frequency domain, now we can just multiply it, multiply the Fourier transform, or multiply the Fourier transform, and we will get the result. So our thing will be easy. So how this thing can be interpolated, like convolution in time to this multiplication in frequency. Convolution means both multiplication as well as addition, but when we are choosing to frequency domain, we are just doing the multiplication. So that is the only concept. Okay, similarly the CMP is for DFT, that is discrete Fourier transform, and DCT. No need to again look into detail, but this is what you need to remember, CMP for Fourier transform. So again I am repeating, what is the CMP? That is convolution multiplication property. Okay, it's a fundamental principle in signal processing and transform theory. It describes how a convolution in one domain becomes multiplication in the frequency domain. So earlier there is a convolution convolution operation that we are doing, that is spatial domain or time domain, but whenever we are choosing into frequency domain, we are doing the multiplication operation. So our thing will be much easier. So that is known as this property is known as convolution multiplication property, or CMP. Okay, now this is the 2D transform. Now our image is a 2D data. Okay, so 2D signal. So 2D transform is a 2-dimensional because it has width as well as the height. So that is why our image is a 2D data. Okay, so 2D image transform, and image transform, it converts from one domain, same thing, usually spatial domain, to this another domain, that is frequency domain. Okay, so same thing. So yeah, this is how you write this signal in a 2 domain. Okay, earlier we have only this lambda I into bi into bix. Okay, but now we have bxy. Okay, and again we have two sigma that is written. One sigma is for ith direction and another sigma is for jth direction. That means we have two dimension. So that is why the transform we will be using it as 2D transform. Okay, so this is the 2D DFT formula. Same thing, you will be have one basis, and now as our function has 2 dimension x as well as y, so that is why we have this two things, that is this is y from 0 to n minus 1, and that is this vertical or this height axis, and x is equals to 0 to m minus 1, that is the width axis. Okay, so this is the formula of 2D DFT. So this is the concept, nothing important. DCT, DFT means sine as well as cosine. DCT means we are only dealing with the cosine. So here only cosine term will be left. Okay, so this is the thing. Now overview. So this is the thing. This is the chart that I have given. You can just read it. I will be giving the slide, so you can just read it. So these are the different terms that are discussed in the image transform thing, and these are the domain where you can apply. This is the description and this is the key use. So the most important thing is till now you must be wondering why we are doing this transform. We are doing this transform, but actually why we are doing this transform? So the image transform that we use it for analysis, because earlier in time domain it is very difficult to analyze the frequency, etc. So if we are converting it to a frequency domain, so we can do the analysis easy. Second thing is compression, because whenever we are doing this Fourier transform, it is divided into sine as well as cosine. So if we just left one term, like if we are just dealing with the cosine term, so what will happen is we can compress the image. Okay, so that is compression. We can also do filtering, because CMP or convolution multiplication property of this transform, it helps in doing the convolution operation much easier. So filtering can also be done. Similarly, you can read all of this. So this is the thing that I have written, that analogy to remember. So think of image transform as changing the perspective. Spatial domain, you see where the changes happen, like edges, line, etc. Frequency domain, you see how fast the change happen. So this thing you should always remember. Okay, so I know these things are a little bit confusing, maybe little bit confusing to you, because so many formulas, etc., etc. But I have given all the definition, as well as I have given all this chart also, and this analogy you have to remember. So spatial domain means you see where the change happen, but frequency domain, you see how fast the changes happen. Okay, so this is the theory portion. Okay, so no need to worry much. So only you have to you need to know what is a image transform, why we are doing the image transform. There is a image transform, or there is a transform known as Fourier transform, that is very popular, because it converts your signal or image into two domains, sine as well as cosine terms. Okay, so that is Fourier transform. Then Fourier transform, then you need to remember what is the CMP. That is a property that that makes our life easier, because whenever we are changing spatial domain to frequency domain, our convolution operation will become a simple multiplication operation. So it will make our life easier. So then 2D transform. 2D transform is nothing. 1D transform, whenever we are doing transform for a one dimension function, that is 1D transform. 2D transform means whenever we are doing the transform for a 2D image, that is 2D function, that is 2D transform. So image is a 2D image is a 2D function, so that is why for image we do this 2D transform operation. So this is, and what is a transform? Simple, from spatial domain to this spatial domain or time domain to this frequency domain is known as transform. Okay, this is the basic concept that you always should remember. So is it clear, or some portion you got at least? Okay, so I hope
I have one
yeah, please.
quick question. Is exactly what about your teaching, that is excellent. I was looking for some reference. Is it possible that quickly you can give us some reference, means very standard and basic reference, where we can find these things?
Okay, okay. So I will try to give you a book link. Okay, and that will be easier for you. So I will be giving all the material, and the material I will give you a book PDF. That will be easier for you for all these theories. Okay. And second thing, the slide that I have made, it is very you can say it is very basic, but it has all the definition, etc., that is written very clearly, so that also you can follow. Okay. Okay, so by this we will be moving on to our question answer session. Now the question answer session, this question will be very much similar to your assignment, not exactly like your assignment, because assignment you have to solve by yourself because it is graded. So this question will be very much similar to assignment. So in each question, what I encourage you is to give the, at least guess the answer. After that we can discuss it. Okay, so this is the thing. So let's move on to the question answer session. Okay, so topics on which week 1 assignment question are based: image, geometric definition of image, all the image processing concept, and then image transform. Okay, so this is the first question. So consider the following 5 into 5 image array to answer the following question. What is the value after histogram equalization at location shown with the with an asterisk mark in the image array. So this is the asterisk mark that is shown in the image. So it has been told what is it has been asked what is the value after histogram equalization at a location shown with the asterisk mark in an image array. So can anyone tell how to approach this question?
We have to count number 3.
Count number 3 and not others.
Okay.
So you have to count all the pixel values. Okay, so let's give you the answer. Yeah, so yeah, your first approach was right, but to count all the pixels, not just 3. Okay, 3 we will focus at the end, but we have to first make a table. Okay, table of all the pixel values and the frequency, how many time it is occurring. For example, 0, how many times 0 is occurring? 3. Okay, 1, how many time 1 is occurring? 1 1 1 3. How many time 2 is occurring? 2 2 2. Again 2 2 2 2 2 2 3 4 5 5 times. Similarly 3 4 times, 4 3 times, 5 3 times, 6 4 times. You can check. Okay, now what we will do, we will do the cumulative sum. Cumulative sum is nothing but you have to just add, like this is the first thing, so 3 is written. After this 3 plus 3, so 6 will be cumulative sum. Then 3 plus 3 plus 5, that is 11. 11 will be cumulative sum. 3 plus 3 plus 5 plus 4, that is 15. 18 21 25, etc. Now we have to normalize the sum. How the normalization occur? Normalization will occur, that is the cumulative sum into cumulative sum divided by the last cumulative sum into your L minus 1. Now what is this L minus 1? L means the maximum value of your pixel. Okay, that is L. So here what is the maximum value or the value of your pixel? So here the pixel is ranging from 0 to 6. That means there are 7 pixel. So 7 minus 1 into 6. So how this normalized sum is calculated? That is the cumulative sum for this pixel, that is 3 into L minus 1. L minus 1 will be common for everything. So that is 7, total 7 pixel are there. So 7 minus 1, that is 6, divided by the cumulative sum at last, that is 25. Okay, so by that you can do the normalized sum. Once you do the normalized sum, these are the values. After that, how the new pixel can be formed? New pixel can be formed by just rounding of the normalized sum. 0.72 rounded off to 1, 1.44 rounded off to 1, 2.64 rounding off to 3, 3.60 rounding off to 4, 4.3 to 4, 5.045 and 6 rounded off to 6. Now here what has been told, what is the value after histogram equalization equalization at location shown at the axis, that is 3 pixel. How we can do the, okay, someone is joining. Yeah, so third pixel or 3 pixel, what is the new pixel value that is coming? So that is, so our 4 will be the answer. Okay, so 4 is the answer. So is it clear to all of you?
Sorry, sir. If you don't mind, can you please repeat how to calculate normalized sum?
Yeah, normalize sum
Yeah,
the for 0 pixel. Okay, for 0
yeah,
pixel, what is the cumulative sum? What is the
three,
frequency is 3. Okay, frequency sorry what is the, sorry, cumulative sum, the cumulative sum is 3. Okay, for
three.
this 0 pixel, cumulative sum is 3. 3 divided by total cumulative sum at the last pixel, that is 25, into how many pixel are there, that is 0 to 6, that means 7 pixel are there, 7 type of pixel are there. L minus 1, that is 7 minus 1, that is 6. So 3 into 6 divided by 25, that will be coming at 0.72. Okay, how you can calculate for this for this 1 pixel, that is 6 into 6 divided by 25. Now how you can calculate for this, that is 11 into 6 divided by 25. So that is how you can calculate the normalized sum. So is it clear?
Yeah, understood, sir. Thank you.
Okay, so is the sum clear to all of you? Important sum regarding histogram equalization. So now, if question will be asked on histogram equalization, can you do it? You can do it, right?
Yes.
So any doubt regarding this question, you can please ask. Frequency you understood, right? What is the frequency? That means 0 is coming how many times? So 0 is coming 3 times, that is why 3. Cumulative sum, like 1 is coming 3 times, but previous there is another 3 for 0, so 3 plus 3, that is 6. So that is why cumulative sum. Normalized sum, that is cumulative sum of for that pixel into L minus 1. L is number of pixel, that is 7 type of pixel is there, 7 minus 1 is the 6, and divided by this cumulative sum at the last, that is 25. So that is normalized sum. And then new pixel, it is very easy, that is rounding off whatever you got the normalized sum. 0.72 rounded off to 1, 1.44 again rounded off to 1, 2.64 rounded off to 3, 3.60 rounded off to 4. Okay, and we need to find out the new pixel value after histogram equalization for the third pixel, asterisk mark, that is third. So third pixel we need to find out. So 4 is the new pixel and 4 will be your answer. Okay, so is it clear?
Sir, assignment.
Yeah, yeah, please. Yeah,
What is the assignment, sir?
assignment, you can get the assignment in your swayam portal. Whenever you will be opening it, you will get the assignment questions. Okay, assignment question you need to do yourself, okay, because that is graded. But what I am doing is I am solving very much similar question relating to your assignment. So whenever you will be doing assignment, that will be very easy for you. Okay, so is it clear?
Okay, sir.
Okay. Okay, so our first question is over. Now let's move on to the next question. Okay, so this is the next question. Yeah, two time note is written. Note that probability of a normal variable p z greater than 2.5 is 0.062. X is normally distributed variable with mean mu equals to 30 and standard deviation sigma equals to 4. We have to compute p x lesser than 40. P is probability, okay, x is the this random sample, okay, z is the z score. So can anyone tell how to approach this question? So no guesses. Okay, okay, so let me show the answer. Yeah, so first you need to compute the z score, okay, because our given condition is given with respect to z. So how you can convert x to z? So x to z can be converted by this z score, okay. Z score, how z score is computed? Z score equals to x minus mu divided by sigma. So if your x is 40, then how you can calculate the z? That is 40 minus mu, that is given, that is the mean. 40 minus 30 is 10 divided by standard deviation, that is 4. So 10 divided by 4 is 2.5. Yeah, formula of normal deviation. Yeah, so z you can calculate by that. Now z is clear. Now what we need to do, p, we have to find probability of x lesser than 40. That means we have to find probability of z lesser than 2.5, because x is converted to z by this formula, okay. Now we have been given p z greater than 2.5 is 0.062. Now we can find p probability of z lesser than 2.5. How? By 1 minus the probability of z greater than 2.5. So 1 minus 0.062, that is coming 0.938. So 0.938 is your answer, that is option B. Okay, so again, is it clear to all of you? Clear, right? Yeah, so let's move on to the next
Sir,
question.
kindly,
Yeah, please
sir, kindly repeat the again, please.
repeat the procedure. Okay, so first you need to understand what is given here, okay. So yeah, so where's my pen? Yeah, so this is the thing, okay. So first you need to understand what is the given here. Okay, so what is has been given, you have to find out, what has been, what you have to find out, you have to find out probability of x lesser than 40. You have to find out what is given, probability of z greater than 2.5, that is given. So ultimately what you have to by seeing the question, what you can understood, you have to convert this x to z. If we can convert this x to z, we can find out the answer. Because if if probability of x greater than 40 is given, then we can easily find out probability of x lesser than 40. How? 1 minus probability of x lesser than 40. Okay, that will be very much easier. But now what has been given is probability of z greater than 2.5 is given. So you have to first convert x to z. How you have to convert x to z? Z will be equal to x minus mu by sigma, that is z score. Okay, z score, how it is calculated? Z equal to x minus mu by sigma. Now is the mu given? Yes, mu is given, that is 30. Is the sigma given? Sigma is also given, that is 4. So you can convert this 40 or x equals to 40 to z. So when x equals to 40, your z is 2.5. Now the analogy is, we need not find probability of x lesser than 40, but that is equal to probability of z lesser than 2.5. We are already given probability of z greater than 2.5, that is 0.062. Now we can find out probability of z lesser than 2.5, that is 1 minus probability of z greater than 1.5, that is 1 minus 1 minus this probability of z greater than 2.5, that is 1 minus 0.062, that is 0.938. Okay, so option B is your answer. Okay, so nothing, you have to just convert x to z. Once you convert x to z, the question is, it is very much clear, because z is greater than 2.5 is given, so you can easily find out probability of z lesser than 2.5. Okay, so is it clear?
So how to calculate in between values? Suppose if you have to give a values in between two values, how can we calculate? Compute p of x is in between. So if it is x is less than 40
Yeah,
and somewhat 36 less than or equal to x less than 40, like that, how can we
then the
calculate?
information will be given, you cannot calculate like that. Okay, z score is always effective when this lesser than values or greater than value you need to calculate. Okay, there also, if it is given that p let's say p z greater lesser than 1 is given, and p z greater than 2 is given, then you can calculate, right? So that you can calculate. So for that, the 2p probability of z value should be given. Okay,
But in our assignment question, we won't they won't give any values, but they have to ask the question in between. How can we calculate that?
z values is not given.
Yeah, one is greater than value will be given, and
Yeah.
lesser value is not mentioned over there. But they are asking compute the value in between values. That's why I'm asking the questions.
Okay, so you solve it yourself, and then next class we can discuss. After your assignment questions are being graded, after that we can discuss. Okay. One is a z score table. So if z value is not given, or any mean or standard deviation is not given, then
Okay.
you have to refer to your z score table. From that z score table, this probability is already there. Okay, so that is a log table. So there
But
the
it is if
yeah.
it is not given in our exams, no. So how can we calculate
No,
if we're not?
it will be given. No doubt regarding that. Okay.
Yeah.
Yeah, it would be given. Okay. Now let's move on to the next question. Okay, so let's move on to the next question. So consider two images of size 16 into 16, I1 and I2. I1 is 192 and 64 pixel for foreground and background respectively. Okay, I1 is given is 192 pixel for foreground, 64 pixel for background, and I2 64 pixel for foreground, 192 pixel for background. One pixel is selected at random from one of the two images, and it is found to be a background pixel. Find the probability that it was drawn from image I1. So can anyone tell what is the concept for this question by reading the question? Yeah, please. It is a question of which part? Bayes theorem, right? Bayes theorem or Bayes classification, right? Okay, yeah. So this is a simple question of Bayes theorem or Bayes classification. So first we need to just we are given, okay, I1 I2 of this 256 pixel, I1 as this 192 for foreground, 64 for background, I2 64 for background, 192 for foreground. So one pixel is selected at random of the two image, the pixel is found to be background. So we need to find this, that pi1 given the pixel is background. So that we need to calculate it. So how we will proceed it? This is a simple question of this Bayes theorem. So let's say B as the pixel of background, because we are interested in background. So B as the pixel of background. So I1 is the pixel from image I1 and I2 pixel from image 2. Then pi1 pi2, because we have two image and we are selecting the two image, so the probability will be half. Okay, so that is why 0.5 b by I1 for this I1 64 background pixel are there, so 64 by 256. Okay, so because 256 is the total number of pixel, that is 0.25. Probability of B given I2, that is 192 background pixel for I2, so that is by 192 by 256. So answer is coming 0.75. So you have to do this Bayes theorem, because you have to find I1 given the background. Okay, we know the B by I1, but we do not know the we know the P B by I1, but we do not know the P I1 by B, that we need to find out. So how we can find out? That is P B by I1, that we can B by I1, that we know. P I1 also we know, divided by PB. So how PB is calculated? PB is calculated by this, PB by I1 into PI1, PB by I2 by PI2. So by this we can calculate PB. So probability of B we got, probability of B I1 we already got, probability of I1 we got. Okay, so by this we can calculate the probability of I1 given B. So that is coming 0.25. So 0.25 means 1 by 4. So option A is your correct answer. Okay, so this is a simple question of the Bayes theorem. Okay, so is it clear to all of you? Yeah, so it is a simple question of a Bayes theorem. So let's move to the next question. So question number 4. So again I think it is a Bayes theorem question. So an image taken using a camera can be enhanced by different techniques. Suppose a software is developed which can detect if an image has been enhanced or not with accuracy 96%. A survey is done and it is found that 75% of all images are enhanced. If the software predicts that an image is enhanced, what is the probability that the image is actually enhanced? So again we are given the software detects correctly with 96% accuracy. 75% of images are actually enhanced. So how we will formulate this? E, we will take image as enhanced, not E, image not enhanced, P, the software predicts enhanced, and we have to find P E by P, that is enhanced given it is predicted by software, that we have to find out. So again the simple Bayes theorem, that is known probability, that probability enhanced, that is 75% enhanced, so that is by 0.75, not enhanced, the remaining 25% not enhanced, so 0.25. Probability P by E, that is this predicted by software, and enhanced, that is 0.96, that is given. Okay, 96% accuracy, that is same thing, and probability not enhanced, that is the remaining 1 minus 0.96, that is 0.04. Again you have to just apply this Bayes theorem. Probability of enhanced divided by probability of enhanced given it is predicted by software, that will be given by this formula. We have P by E, that is already given 0.96. We have PE, that is 0.75. We have to just compute this PP, that is probability that is predicted by software, that can be find out by this formula, and by this if we got this PP, P or probability of predicted by software, we can get the probability of enhanced image given that it is predicted by software. So the approximately it is coming 0.9863, that is option C is your answer. Again it is a typical question of your Bayesian classification or Bayes theorem. Okay, so this is the thing. So is it clear to all of you? Same questions, similar kind of question. So base theorem is very important, so you just need to understand it. Okay, so this is the thing. So let's move on to the next question. A continuous time signal is given by x t e to the power minus 2t ut. Its Fourier transform x j omega is given by. So this is the time domain and this is the frequency domain. So we are doing the Fourier transform. So we are converting from this time domain to this frequency domain. This t is for time domain, j omega is for frequency domain. Okay, so this is a simple question of this Fourier transform. This is a standard approach, so you need not to look at it. It is better you do with the simple formula. So this is your signal. Okay, this is a signal in time domain. E to the power minus 2t ut. Ut is a unit step function. Unit step function means the signal exists only for t greater than equal to 0. Means t greater than lesser than 0, there will be no signal at all. This is ut what stands for. Okay, so this is the thing for ut. Now this is your signal. Fourier transform, how you can get e to the power whatever signal ut into this is your as j omega is your basis, so e to the power minus j omega dt. So just solve this and you will get the answer. Now how we can solve this? I have told you that your unit step function means your signal exists only for t greater than equal to 0. So for t lesser than equal to 0, there will be no signal. So that is why minus infinity to infinity will be converted to 0 to infinity. E to the power minus 2t, e to the power minus j omega t dt. You just add up minus 2t plus minus j omega t. So minus you can take common 2 plus j omega t dt. Okay, and then you can do the simple integration. You all know integration. E to the power minus e to the power alpha t. How we can integrate? E to the power alpha t is e to the power alpha t by alpha. Okay, so similarly e to the power minus 2 plus j omega t divided by minus 2 plus j omega, and your limit from 0 to infinity. You just solve it and you can easily get this 1 by 2 plus j omega. So this is the most important Fourier transform formula that you always have to understand. That is function into e to the power minus basis. What is the basis here? J omega. That is why e to the power minus j omega t dt. Just solve this and you will get the answer. Okay. And there is a standard approach also, that formulas are already known. So there is a formula for whenever your signal is of the form this, so your Fourier will be converted to this. Okay, Fourier transform is this. So no need to just memorize formula and all. You just memorize the core formula for Fourier transform and you will get the result. Okay, so this is 1 by 2 plus j omega is the answer. So option A is the answer. Yeah, option A is the answer. Okay, so is it clear? Clear, right? Okay, nice. Now question number 6. Consider a binary image with a small fully filled white circle on a black background. Binary image means two kind of pixel, 0 and 255. 0 means dark, 255 means white. Okay, so these are the two pixel. How does this image looks like after applying image gradient operation? Same as the original image. Image gradient operation means we are finding the edges where there is a more you can say abrupt change in intensity, right? So that means whenever we will be applying the image gradient, we will be detecting the edges. Okay, so our original image is nothing but a black background with a white circle. Okay, so what will happen? Same as the original one. So no, it will never happen. A thin line surrounding the boundary of the fully filled white circle. I think this is the answer. A thin line surrounding the boundary of the whole circle, whole image. No, that is not the answer. And this is also wrong. And an image with a white dot at the center. This is also wrong. So option B is your correct answer. Okay. So let me summarize this. So yeah. So image gradient means what we are doing, we are finding where there is a significant change in intensity. So given binary image, a fully filled white circle on a black background, pixel value 0 and not 1, 0 and again 255, okay, 0 and 255, 255 for white, 0 and 255, okay. Now applying image gradient inside of the white circle, all this 255 will be 0, and all this 0 will be 250, all this 0 back 0 0 yeah, the inside of the white circle is all inside of the white circle all 255, so that means 0 gradient, black background, that is 0, again no change, but wherever but at the boundary between the white and black there is a sharp change, that is 0 to 255 or 255 to 0, so that is a strong gradient. So the edges will be detected only at the boundary of the circle. So option B is your correct answer, okay. So option B is your correct answer. So is it clear to all of you what has been told in the question? Clear, right? So again I am repeating, we have an image, black color image, okay, someone is joining now. Okay, now we have a black color background image, in between there is a white circle, okay. We have been asked if we apply the gradient operation what will happen. So we know applying the gradient operation what will happen is we detect the edge, okay. The edge will be detected where there is a sudden change in sudden or abrupt change in the gradient, okay. So then that will be your edge, okay. So where the edge will be found, where there is a first option same as the original image does not make sense, because edge will be detected, the edge will be detected, but where it will be detected, it will be detected where the circle is completing, okay, or there on the boundary of the circle and the black background, okay. A thin line surrounding the boundary of the whole image, again does not make sense, and last an image with the white dot at the center, again does not make sense, okay. So option B is the correct answer, okay. So logic is gradient means you are detecting the edges, okay, and where the edge is detected, where there is a abrupt change in the pixels, okay, abrupt change in the pixel intensity value, so that there is a edge present, okay. So this is the question number 6, okay. Now let's move on to the next question. Consider the following 3-bit grayscale image. 3-bit, actually our image is a 8-bit image. 8-bit image means we are representing our pixel 2 raised to the power 8. So 2 raised to the power 8 means 250 256, okay, that means 256, that means 2 to the power 8 means this is 2 to the power 8, okay. 2 to the power 8 means 256, that means the pixel value is from 0 to 255, okay. That is how our image is represented, but here they are representing their image by 3-bit, okay, not 8-bit or 1 byte but 3-bit, so that will be 2 to the power 3. 2 to the power 3 means 2 to the power 3 is 8, okay. 2 to the power 3 is 8, that means 0 to 7, so your pixel value will be between 0 to 7, okay. So 0 to 7, okay, consider what value, okay. I think there is a mistake in the question here, okay. I think okay, no, 0 to 7, yeah. So here this has been asked, what is the value when vertical Sobel operator and horizontal Sobel operator are applied on the pixel, okay, on this pixel. What is the thing, yeah. So 0 to 7, so that is why the pixel value you can see from 0 to 7 only, because it is a 3-bit image, so that is why pixel value are from 0 to 7. So this is the logic. Now the question has been asked, what is the value when vertical Sobel operator and horizontal Sobel operator are applied on the orange pixel, that is 5, okay. So as it is a 3-bit grayscale image, and our filter for this pre-bit as well as Sobel operator are 3x3 filter. So first we need to for that we need to focus only on this reason, okay, 3x3 reason. For this 5 neighborhood, okay. So 5, what is the neighborhood? This is the neighborhood, and we are only focused on 3x3 pixel. This is the portion on which we are focused at, Okay. Now we have been told what is the value when vertical Sobel operator and horizontal Sobel operator is applied. So we need to know what is the vertical Sobel operator and what is the horizontal Sobel operator. So let's go there. So yeah. So what is a vertical Sobel operator? This is a vertical Sobel operator 1 to 1 0 0 0 minus 1 minus 2 minus 1. What is the horizontal Sobel operator? Minus 1 0 1 minus 2 0 2 minus 1 0 1. So these are the two filters we need to remember for this Sobel operator. Okay. So yeah, so where we were, so we were at this position. Yeah. So how we will approach the question? Very simple. First we extract this portion, that is the neighborhood of 5 as a 3 cross 3 filter, because Sobel as well as this prevent, that only gives 3 cross 3 filter. So we need to first extract the 3 cross 3 neighborhood around your orange color pixel, that is 5. Okay, so this is the neighborhood that we have extracted. Now we will see what is this horizontal Sobel operator. This is our horizontal Sobel operator and this is our vertical Sobel operator. Now we just have to apply this Sobel operator. How we will apply? Simple operation, that is convolution. Okay, so very simple, that is minus 1 into 0, 0 into 0, 1 into 3 plus this minus 2 into 1, minus 2 into 1 plus 0 into 5 plus 2 into 2, then minus 1 into 0, 0 into 3 and 2 into 1, and we add up, we get 7. Similarly, we will apply this horizontal operator. We will just do the convolution operation, that is multiplication of pixel and then addition, and we are getting minus 3. So option B is our correct answer. Okay, so for this question we just need to remember what are Sobel kernels, vertical and as well as horizontal Sobel kernels, that we need to remember. And once we remember that, it is very easy. Okay, just we need to do the convolution operation or masking operation. Okay, so by that B is our correct answer. So is it clear to all of you? Clear, right? Okay, so I hope it is clear to all of you. It's a very important question, it might come. Okay, so I hope it is clear to all of you. Okay, now question number 8, consider the direct linear transform algorithm for a point correspond to xi dash to xi, okay, which involves the following equation: homogeneous coordinate xi dash xi transformed an original 2D projective space where h is a projective transformation x dash tilde hx. Okay, so choose the correct option. Okay, so actually this is a concept that we will be learning in the coming class, but to make your things easy, actually x dash tilde hx means the two vectors are equal to up to scale, and x dash is there and hx is there. Okay, so for both this vector, what will happen is the direction will be similar. Okay, x dash equals to lambda hx, this is what it implies. So direction will be same, but what will be difference is the difference can be difference in magnitude. Okay, so this is the difference between x dash and hx. Okay, so this is the difference between x dash and hx. Okay, the direction will be same, and they will be on the same line, but the magnitude can differ. So let's this is a concept that we'll be learning in the coming class, but this is the concept. So vector x dash and xh may have similar magnitude but different direction, so that is wrong. Direction can be same, but direction is same but magnitude can different, so this is absolutely wrong. Vector x dash and xh hx may not be equal. Yeah, that is correct, they have similar direction but different magnitude. So option B is right according to me. Vector x dash and hx may be equal, they have similar direction and magnitude. So actually they can have and they cannot have, because they can have if this lambda equals to 1, then both will have similar magnitude as well as direction. Otherwise they have same direction but different magnitude, so this for me this is wrong. And cross product of x dash and hx, hx is a zero vector. Okay. So cross product, you know what is a cross product? Cross product of two vectors means in a cross product of b vector, that is ab sine theta. Okay. uh, Same direction means the theta angle is 0, so sine 0 is 0. So whenever we are doing vector this cross product of two vector of same direction, having same direction, the cross product will be 0. So option D is also correct. So B as well as D is the correct answer. So this is not clearly for this class, but you can just see the concepts. Okay, the concept is x dash and hx will lie on the same line, that means same direction, but can have different magnitude. Okay, so that is the concept for this. Okay, this need not to be thought of seriously, but this is the concept of this. Okay. Now consider a 3-bit grayscale image with a dimension 32 cross 32. What will be the range of values in its x-axis? So x-axis, y-axis, it will have same range of values, that is 2 to the power 3, because it is represented by 3-bit. Our original image is always represented by 1 byte, that is 1 byte is 8 bits, so that is why 2 to the power 8, that is 256. Okay, so we have 256 values from 0 to 255. But here, as it is a 3-bit image, so so we will have 8 number of values, that is from 0 to 7. Okay, 0 to 7. So 0 to 7 will be our answer. Option A will be our answer. So I hope this is clear to all of you. Okay, this is clear, right? This is one of the basic concept of image, or how pixel values how pixels are represented. So is it clear to all of you? Why our image is from 0 to always from 0 to 255? Because we generally represent it by one pixel, 1 byte. Okay, 1 byte means 2 to the power 8, that is 256 values. So that is why our pixel value range from 0 to 256. But here it has been given 3-bit, that is 2 to the power 3, that is 8. 8 is from 0 to 7. So our pixel values can range from 0 to 7. Okay, so this is the thing. So I hope it is clear to all of you. Now moving on to the next question. Now this is the last question. Consider the following 3-bit grayscale image. What is the value? And vertical pivot and horizontal pivot operator are applied on the orange colored pixel. So again, Sobel operator we have already done. Now we have to do it for this pivot operator. Now we have to first check the neighborhood. So 3 has been highlighted in orange color. What will be its neighbor? This will be its neighbor, 143, 430 and 127. So this is the 3 cross 3 extracted pixel. Okay, this is the 3 cross 3 extracted pixel matrix. Then this is the horizontal pivot operator, this is the vertical pivot operator, and just you multiply this, minus 1 into 1, then 0 into 4, then 1 into 3, plus this minus 1 into 4, 3 into 0, 0 into 1, plus you can calculate. And horizontal after applying horizontal value is coming 4, and vertical value is coming minus 2. So 4 comma minus 2, and option C is your answer. Okay, so option C is your answer. Okay, so horizontal and vertical 4 comma minus 2. Actually, yeah, for horizontal and 4 comma minus 2, actually pivot, vertical pivot and horizontal. So minus 2 comma 4 should be the answer, but as minus 2 comma 4 is not given, so 4 comma minus 2 is the answer. Actually this should be horizontal pivot operator and vertical pivot operator. Okay, so that should be the question, and your answer is 4 comma minus 2. Okay, so the question, it has little bit of mistake, but by calculation we can understand. So 4 comma minus 2 is your answer, or option C is the correct answer. Okay, so this is the thing. So is it clear to all of you?
Okay, sir.
Yeah, please.
So actually,
Yeah.
um, I have not gone through the videos
Okay.
actually. So you have Immediately you upload, no sir, because we have to do the first assignment.
Yeah, I will upload after the class gets over. Okay.
Okay.
Yeah.
Because I will go through that and
That is my
we'll go.
content, but sir's content is already available in your NPTEL SWAYAM portal. Okay.
So the content covers all these problem solving and all. That is the theory. Will it cover all these things, sir? You have not.
Yeah, it will cover all these things. For
Uh,
me, I am more focused on the question part. Okay, that is actually my job. But before that, I always like to discuss some of the theory, etc. So it will be more
uh,
easy for you to understand.
Sir,
yes.
Yeah,
We will go through the videos, sir,
yeah,
before
yeah,
we attend
yeah,
assignment.
yeah. Please.
sir, can you please provide this PPT or
Yeah. It will be provided. I will after this class. Just give me more 10 minutes. Okay. I am already late. I know, but this is the first session. All and again, guys joined late, so that is why 10 minutes. Give me 10 minutes more, and I will say everything. Okay. So
Sir,
yeah.
sir, tomorrow also we have two classes, right? Two sessions are same or different sessions?
Actually, the question will be similar. Question will be similar. The three TAs they will cover the same type of question, or maybe the same question, similar question, or maybe the same question also. But everyone has their own way of discussing things. Okay, so you can join or you cannot join. If you, it is better out of this three lecture. At least you join one session. Whatever you like, at least you join one session. Other two session you can see the YouTube video, because YouTube video of all the session will be provided to you. Okay.
Okay, sir.
Okay. So this is regarding the theory as well as question. So before we commence the class, it will be better if I show you some of the codes regarding this, because coding it will not come in your exam, but computer vision you cannot do computer vision without codes, right? So that is why what I have done is I have formulated some of the codes for you, and you can just see those codes. So these are the codes. Yeah, these are the codes that I have given, like image representation. Let me open one code. It is visible to all of you, right? Is it visible?
yes,
First
sir.
question. Yeah, so this is the code, like image representation codes, like how an image can be represented into different type of image. So this is your original image, and with the help of code, this is your red, green and blue channel. This is your grayscale image, and this is the binary image of threshold t equals to 127. That means lesser than 127, that is black, and greater than equal to 127, that is white. Okay, so that is the code for your image representation. What you this I have made this notebook very well by commenting each and every step. Okay, so you can just open this. I will give you the link. You can just open this code. There will be something coming here, that copy to drive. That you just copy this code to your drive. You run this code and you can see the result. Also you can modify the code and you can play with the code. Okay, so this is regarding this image representation. Okay, so I am generally doing the coding in Python language. So this code is of Python language. So Python, we have all these predefined libraries. Okay, so predefined libraries, you just need to call these libraries, and all this function can be performed. Okay, so this is the one thing. Image histogram analysis, let me show this also. Actually it will take some time to load. So yeah, this is the image histogram analysis. Okay, so this is the thing, like this is the image. Okay, and this is the image histogram. Okay, so red, green and blue channel, this is only blue channel available. The red and green channel is not available, so that is why it is only showing for this blue channel. Okay, so you can see the images. Okay, you can see the histogram that is forming. This is the pixel intensity value from 0 to 255. Okay, 0 to 255, and you can see that for some pixel there is a peak. That means there are frequency. For other pixel there is no frequency. Okay, so this is the image histogram, how you can get the image histogram. Again, this is a Python code, so there is a library for this. That is, this is the library C histogram. So you just call this function, and you can just call this function, and your image histogram can be displayed for this image, any image that you will give. Okay, similarly there is a binarization thresholding. So let me just show you for better understanding. Yeah. Yeah, so this is another code for your this binarization. So this is a random threshold, so does not make any sense. This is a global threshold 127. You can see this is the Orsu method. That is this two are this your automatic threshold. So again we are doing this. We have this all this libraries in our this Python libraries and in the libraries we all have this function. So just call this function like this Gaussian maximization, etc. Just call this function and the thing will be performed. Okay, so this is the thing. This is how we are doing the thresholding. So this is the thresholding. Okay, t is equal to 127. This is how our thresholding. By this thresholding, this is how our image is looking. Okay, and by this Orsu method, how our image is looking, and by this your GMM, that is this expectation maximization algorithm, how our image is looking. Okay, so Orsu method by this expectation maximization, the thresholding that is coming is 188. Okay, so 188, you can see this is a automatic thresholding, whereas this is a random thresholding, that is t equals to 127. So you can easily see the differences. Okay, so this is another code. Similarly, there is image equalization. So let me open this also for your convenience. Yeah, so this is image equalization. So this is the original image. So you can see this histogram. Okay, so there is peak for only for this reason. Okay, but whenever we are doing this equalization, see we are just we are just spreading our peaks to all the intensity values. So what it is having is, earlier this is our image, now it is contrast enhancement is happening. So now this is our resultant image after histogram equalization. Okay, so this is the thing. Earlier we have a peak at only one place, so that is why there is not enhancement is not good. But now as we have peak at different intensity, so that is why our image is more our image is more enhanced. Okay, so this is the histogram equalization. Okay, similarly there is manual on automatic component grading. Yeah, this we can see, or yeah, this also we can see. Let's see. So these are the things and it will take a few minutes. Yeah, so this is the thing. So you can yeah, this is the thing. So now thresholding, see there are two threshold, one is this, one is this. So by this, see this is the original grayscale image, and this is the our multi-level segmentation. Okay, this is multi-level segmentation, and this is done by automatic thresholding, that is Orsu method we have applied. So these two are the threshold it has identified, that is T1 that is 55 and T2 that is 77. Okay, so before that we have blue from this T1 to T2 we have this I think green, and then after that we have this I think this blue color. Okay, so that is the multi-level thresholding or segmentation. Okay, so this is and the code. Similarly component leveling is there, no need to, yeah, this is important. That is this edge detection. Okay, edge detection by whatever like Sobel, Privet, etc. So you can easily see the results. So this is our original grayscale image. This is the vertical privets. You can see this vertical edges are seen. This is the horizontal sorry, this is the vertical privets. So I think this names are changed. So this is horizontal, this is vertical actually, and this is the resultant. Similarly, this vertical, horizontal, and this is the resultant. This is the privet operator, and this is the Sobel operator. Okay, and this is the resultant gradient. Okay, so this is the thing. This again everything Python we have this predefined libraries, and in the libraries we have this function. We just need to call the function and we can get this results. Okay, and for each code what I have done is I have annotated all the steps, as well as I have given all the comments, so that this code is very much self-explanatory. So you just need to go to this code. You just for you there will be something written here, copy to drive. You just copy to drive, and then you can perform this operations. Okay, and also you can make changes if you want. So these are the basic, or these are the basic codes or source code. Okay, similarly you can see the other codes also. Okay, so this is these are the codes. So is it clear to all of you? This codes also I have given to you all. So is it clear? Okay, now for links, right? So this is the YouTube channel. This is my YouTube channel. Okay, this is the YouTube channel where I will be uploading this video, whatever we have discussed in this class. And there is another thing called, yeah, there is this link. Okay, this is the drive link where you will get where you will get both the codes as well as the PPT. Okay, presentation for today. Okay, so these two links are important. And another link also, let me give you this link. So this is the master link actually. So let me so this is actually the master link. Yeah, so let me give you this link also. This is the master link where you will find the content of all the TAs, not just me but all the 3 TAs. Okay, so these are the 3 links. One is the YouTube channel link, second is the drive link for my content, and third is the master link for all the contents as well as video for all the TAs. So these 3 links you always should keep with you. Okay, so by this I am ending the session for today. I hope I have given you something for this class. Yeah.
Sir,
Yeah,
you are
please.
giving the links, no, sir?
Yeah,
In
yeah.
that, huh?
Yeah.
In that, in your this thing, YouTube links also you will be giving, no?
Yes, yes. This is the
Huh?
YouTube channel link. Okay. This is the second link is your this drive link where I have
No.
uploaded the presentation as well as code. And third is
You are
the Google
you
Sheet.
are
Okay.
sending to your emails, or you are keeping these links in our emails. That announcements is there, no announcement. Are you keeping these 2 links of YouTube's? Where do you keep, sir?
No, no, no. Actually, I have given here, so you can save it for now. Otherwise, what you do in the Swayam
Please
portal.
send it email, sir, or announcement. Course announcements it is there, no?
Yeah, yeah,
You can
yeah. I
keep.
am telling you. Just listen to me first. So in this Swayam portal, wherever you have this weeks, there will be one thing written at the bottom after the week is a problem solving session. Whenever you will open the problem solving session, let me again share my screen. Okay, so yeah. So okay, I think that will not solve you. Yeah, so let me share my entire screen. Yeah, so whenever you will be yeah, whenever you will be open that problem solving session link, you will get something like this web sheet. Okay, in this web sheet what I will do is, this is my content, so I will give the YouTube link for this week 1 video. I will give the presentation folder link for the entire session, and then this meeting attendance that is not related to you. Similarly, this is for the second tier that will take the class for today. Similarly, there will be a thing for the third tier. Okay, so you just
Okay.
visit your Swayam portal, and in the Swayam portal below the weeks there is something will be written like something will be written called problem solving session. You just open this and you will be redirected to the spreadsheet. In this spreadsheet you will get all the content. Okay,
Okay, sir.
so
Thank you.
I
Thank
will
you.
be uploading my content tonight only. Okay, so there, otherwise this 3 link I have also given in chat, you can save it. Okay.
Hello, sir.
Yeah, please.
Sir, actually, the content, all those things available in SARS video. So we must expecting more thing in a problems. So because
Yeah.
all the questions are in a problems only. So you have to concentrate more on problems. That will be helpful for us to solve our
Okay.
assignment
Yeah, yeah.
questions.
That is why there are 3 TAs are there. So definitely
Okay.
they will, yeah, they will solve problems. All the 3 TA will solve problems. So actually only 10 questions are given to us. These questions are given by them only. So the
Yeah.
question that will be given by them, that only I can solve. So 10 question if I will solve, it will not take 1 hour to get it over. Okay. So that is why I always prefer to first discuss with everyone what we
Okay,
have
and I understand your
yeah
problem, but thing was
what we have discussed in the
expecting
weeks also.
more.
Yeah,
Mm.
yeah, I can understand you, but that is my problem. And second thing is, there are many people in this class, they would not have seen the videos well. Okay, so for that them it will be of help if I will do the summary session first, and then I will focus on the question. Otherwise, if I directly move to the question, I think 2 3 people will answer. Okay, other will be completely blank. So that is also a problem. So that is why that is my method. Okay.
Yeah, okay, sir. Okay, sir. Thank you so much.
So by that I am ending the session for today. I hope it is fruitful, and we
Sir,
will meet on the next Friday. Okay. Yeah,
sir,
please. Yeah, please.
sir, this type of session is happen every week.
Yeah, every week, for every week. Okay. This is week 1 discussion. Similarly, there will be week 2 discussion, week 3 discussion,
Okay, okay,
till
okay.
week 12 discussion. Okay.
Okay,
Hello,
thank you.
sir.
Yeah, please.
Sir, tomorrow lecture is the same or different?
Tomorrow lecture the question will be more or less the similar. Okay, but there can be other see, we all have been given 10 question to discuss with you all. Okay, but we all have different style of teaching. For me, I always prefer to discuss with you some summary, then question, then also some code. Some other TA might take their class in a different way. Okay, so that is how.
So the
So
question will be same or different
similar
question?
question. Okay, almost same. Okay, is it clear?
So, but I'm basically civil engineering background, sir.
Okay,
I have not studied image processing and all. Just an
okay, okay.
easy people the students they study. Huh? So, is it okay? No, if I go through the this thing or
Yeah,
additional information.
yeah. NPTEL is a course for you guys only. Means those who have different departments, those who cannot take the classes in the IITs, for them only NPTEL classes are there. Okay, so NPTEL classes, everything is online. So the teacher has already taken the class. You just see the video, you get through the videos, and you solve the assignment. So that is how NPTEL course works. Okay,
Okay,
so you can
okay.
easily cope up with all. No
Okay.
need to take
Thank,
tension.
thank you, sir.
Okay. So any other doubt? Okay, no doubt, right? Okay, so by this I am ending the session for today. We will meet on next Friday. Okay. So yeah, so bye everyone.